we've learned about motion. And so now there's just a wide range of fun problems that we can do. Fun word problems. So here's a word problem from an exam from last fall. And some people have accused me of writing this word problem, but this was actually written by another instructor. Not every hard problem has to be written by me. It just seems like every problem written by me has to be hard. But this was from somebody else. No, it's not true. I don't write hard problems anymore. They're all fun problems. So the position function of a spaceship is given by this parametric curve, r of t. So in other words, we know our location any time x, y, and z. 3 plus t, t squared minus 7, t squared plus 2, t. At time t equals 0 in seconds, the ship's captain receives orders to turn off the ship's engines within the next 6 seconds. Oh, that's not a lot of time, but okay. And then have the ship coast to a space station located at the point 8926. Determine the time t when the engine should be turned off and give the location at that moment in time. Now, you might be wondering, why do we set so many problems in space? And the answer is so that we can avoid the awkward thing saying, we're not going to worry about gravity. So that's why you see so many problems in space. So we have this spaceship. All right, so there's my spaceship. And currently, it has its rockets on. So it's moving through space. And it's moving along some sort of curve here. So the question is, what are we trying to do? Well, we're trying to get to a space station. So let's suppose we draw ourselves a little space station. Suppose we draw it over here. It'll be sort of a little tube here. There we go. There's our space station. And we're trying to get there. Now, how do we get there? Well, at some point we turn the engines off. So if we think about the physics of the problem, if we turn the engines off, what happens to us? Well, there's no more acceleration, which means that wherever we're going, that's how we're going to keep going. And so we're going to travel along a straight line. Well, which straight line are we going to travel along? The tangent line. So what's going to happen is we need to find the right time so that if we cut our engines, the tangent line gets us to that spaceship. So what's happening here is if we think about the situation, and so we can draw ourselves a picture to help motivate us, what we can say is, okay, I have this parametric curve, 3 plus t, t squared minus 7, and t squared plus 2t. And now we can rephrase it. We say, what do we want? Well, we want a tangent line which goes through a particular point. This point, 8926. So that's our goal. Now, the problem is that there are many tangent lines. So how do we figure out which one to do? And here's sort of my philosophy, which says, if a problem asks me to find a particular thing, say a particular plane or a particular line, what I do is I say, let's find all of them. So we're going to find all the tangent lines, and then we're going to look through our tangent lines and pick the right one. So first step 1, let's get all the tangent lines. All right, well, we can do that. So how do we do that? Well, what do we need for a line? Well, we need a point, and the point we can get from our parametric curve. So our point, and we're going to think of this as a function of t, that's 3 plus t, t squared minus 7, t squared plus 2t. Our direction, well, how do you get direction for a parametric curve? The tangent line of a parametric curve, what do we use? We use the derivative. So we're going to take the derivative. So we go through and take the derivative entry-wise. Derivative of 3 plus t, 1. Derivative of t squared minus 7, 2t. Derivative of t squared plus 2t, 2t plus 2. All right. Well, good. Now, if I wanted one tangent line, I pick a value for t at this point, and I get numbers. If I want all tangent lines, I leave t as it is. And I say, okay, I'm just going to have t be floating around as a parameter at this point. And so I can say, well, in vector form, my tangent line would look like that point, 3 plus t, t squared minus 7, t squared plus 2t, plus some multiple, and I'll use s, 1, 2t, 2t plus 2. Normally we use t, but I'm already using t as my parameter for which time to pick the tangent line. So I just need another parameter for s. All right, that's why we have that. So here's the collection of all possible tangent lines. You pick a t, that gives me a tangent line. And every single tangent line shows up here in our collection. Now, what do we want our tangent line to do? Has to get to that point, 8, 9, 26. So we say, okay, we know we're looking for our tangent line which hits that point. So we say, well, what do our points on our tangent line look like? Well, the x-coordinate would look like 3 plus t plus s. So that's the x-coordinate. So I better have 3 plus t plus s has to equal 8. In other words, I have to pick a value for t to get my tangent line. And once I have my tangent line, I have to get a value for s where I'm on that point. So that's the x-coordinate. T squared minus 7 plus 2 times s times t had better equal 9. And t squared plus 2t plus 2t plus 2 times s had better be 26. So now I have a series of equations and unknowns. Well, that's fine. That's good. Now we get to go back to algebra, and we get to explore. So what are some things we can do? Okay, so we can work towards substitution, solving for one of our variables and plugging it in. Now, that's probably a preferred method here because you'll notice that we have, this is not what we would call a linear system. We have things like t squared and s times t, and when you have that, it gets hard to put everything together. So, for instance, we can come to the first equation. It doesn't really matter which one we solve for. Let's suppose we solve for s. So that would say s would be equal to, subtract the 3, so that would be 5 minus t. Now, we put that into, let's say, the second equation. So we'll get t squared minus 7 plus 2 times 5 minus t times t equals 9. Well, yeah, okay. So what does that give us? That's t squared minus 7 plus 10t and minus 2t squared equals 9. And at that point, we probably want to move everything to one side. We have a nice polynomial in a single variable, so that's good. Let's move everything over to the left-hand side. 0. T squared and minus 2t squared would be a negative t squared on the left. We move it over, it's going to become a positive t squared. Plus 10t, move it over, negative 10t, or minus 10t. Then we have a 9. We're going to bring this negative 7 across by adding. So that would be a plus 16. All right. I think that's right. Okay, so t squared minus 10t plus 16. Well, what does that say? Well, we hope it factors. Does it factor? Yes. Yeah, okay, it does. What does it factor as? T minus 2, t minus 8. Which says that we have two candidates right now, t equals 2 and t equals 8. Can we use any information to help narrow it down to which one of these it should be? Yeah, see, there's this one part that was italicized. It has to be within the next 6 seconds. So this whole computation that we've been doing, the ship's captain had to have finished within the first, apparently, 2 seconds. So the ship's captain must be really good at multivariable calculus. But okay, so we can eliminate the 8. the 8 is not going to work because it falls outside our purview. Will the 2 work? Well, hopefully, but do we know for sure? Yeah, so here's the thing. You have to be careful. What have we used? We've been using the first 2 equations, and so the first 2 equations will be satisfied. If we pick t equals 2, and by the way, what would s need to be? It would have to be 3. So we know that for t equals 2, s equals 3, the first 2 equations are definitely satisfied. That does not mean the last equation is satisfied. So it might be that this ship is doomed. Now, hopefully, the math works out. So what should we do to check? Yeah, we can plug it into the last equation. So we have our t and s, so we just check. So we have 2 squared plus 2 times 2 plus 2 times 2 plus 2 times 3. All right, well, what does that equal? That's 4 plus 4 more plus, well, that's 4 plus 2, which is 6 times 3. 6 times 3 is 18. Plus 8 more equals 26. All right, it's going to work. It's going to work. So if we go along that tangent line, it'll succeed. Now, let's figure out our answer, because we want to make sure we do it. So what does the answer ask? It says, determine the time t. We know the time t. It should be time t equals 2. And then you notice that there's this and. Okay, we have to give the location of the ship at that moment in time. So, what do we do with this time to get the other part of the answer? Plug it in to position. So the ship will be located, and we'll write it as a point. I know this is a vector, but it's a vector that represents a point. So plug it in. 3 plus 2 is 5. Then you get 2 squared minus 7. 4 minus 7, negative 3. And t squared plus 2 times t. Well, that's 4 plus 4, which gives 8. And that's the answer. That's the answer. All right. Good. Well, what's today's topic? In fact, it'll sound very familiar to what we just talked about. In particular, we're going to talk about the motion. So, we know a little bit because we've talked about our problems, but we should go ahead and just be explicit here. So if I have a parametric curve, r of t, well, that's the position at time t. It's recording where are you at. Again, it's been transformed into a vector so that we can do calculus, but there is this nice correspondence between a point and then the vector that goes from the origin pointing to where we're currently at. So it's easy to go back and forth. We talked about the tangent line coming from r prime of t. In terms of motion, r prime of t is telling us how we're changing. So if we think about position as r, how we change is r prime, and that's also known as velocity. So the derivative gives us our velocity, because velocity is change in position. Now, for all you physics nuts out there, there is a difference between velocity and speed. What's the difference between velocity and speed? Well, velocity is a vector, so what information comes with vectors? Direction. So when we talk about velocity, there's an inherent direction built into it. If we want speed, it's a number, it's a quantity. And so when we say speed, we're talking about the magnitude of velocity, which is the magnitude of r prime. The second derivative, r double prime of t, well, that's saying how is velocity changing? And if we say, well, the way velocity changes has a name. That's called acceleration. And so velocity, I should have pointed out, we'll use v of t, and acceleration we'll use a of t. A lot of these things are very familiar because we've seen these before, and we've talked about these in physics. So if we think about the tangent line, that contains information. So it contains information about our position, because our position has the tangent line, and it contains information about our velocity. That's the direction of the tangent line. What if we want to include acceleration? And the answer is we can. So there's something that's called the osculating plane. So what is the osculating plane? Well, it contains position, motion, and acceleration. So it sort of contains even more information. So if we were to plot a curve, which we can do that, so we have our three-dimensional space, and we plot our curve passing through three-dimensional space, then we can say, all right, at this particular point here, well, I have a tangent line. That tangent line contains information about my position and my velocity. If I want to talk about the osculating plane, well, I want to take into account what's happening with acceleration. So in some sense, if you think about this curve as turning, acceleration should be sort of pulling towards the inside. So there's the velocity points in the direction of motion, and acceleration points in a slightly different direction. Now, it could be that velocity and acceleration point in the same direction, in which case you're just moving faster in the direction you're moving. But oftentimes, if you ever see your curve turning, that means acceleration is not in the direction of motion. Now, in case you're wondering why we call it the osculating plane, the answer is right here. The word osculate means to kiss. So it's the kissing plane. It kisses the curve. So you might be hanging out with your significant other at some point later on. You might say, do you want to do a little bit of osculation? And they'll ask, what is that? Something I learned in calculus. You know, how hard, how bad could that be? Well, all right. Of course, I should say you should always osculate with consent. So let's find an osculating plane to a curve. All right, so I need a curve. All right, so what curve do we? Give me some. I need some functions here.
Arctangent.
Okay, arctangent of just t. Is that fine?
T's fine.
All right, arctangent of t. That's great. I need another one. All right, e to the t. We have space. We can expand on that. Plus 2. All right. And last one. T cubed, and there was a t squared, and there was a 2t. All right. Now, there is one thing missing from this question. It says, find the osculating plane to this curve. What was not given? We now have the curve. What else do you need? You need the time. Because the plane is a plane. And so when we're talking about the osculating plane, we have to have where are we kissing? Where is that osculation happening? Okay, so we'll pick time t equals 1. Okay, so that's going to be our time t equals 1. So here we go. Here's our r of t. So if we're going to find the osculating plane, what types of things do we need to find? Well, we're going to need to get to the normal vector of the plane. All right. So we'll need a point. All right, let's talk about point. Can we get a point? Yes, we can get a point. So our point will come from r at 1. So we plug in 1. What's arctangent of 1? Pi over 4. What's e to the 1 plus 2? E plus 2. All right. What's 1 cubed plus 1 squared plus 2 times 1? 4. All right. Yes, we can have points with weird numbers. That's allowed. Good. Now, someone said we need a normal vector. To get to that normal vector, what are we going to need to get to that normal vector? We're going to need 2 vectors. Usually when you're looking for a normal vector, the mantra is, let's find 2 vectors that will be in our plane. What kind of things? What are the 2 vectors that we know our plane is going to have? The velocity and acceleration, because that's what the osculating plane does. It's based off of velocity and acceleration. So if we're going to find that normal vector, we better find the velocity and the acceleration. So that means we get to take derivatives. Derivative of arc tangent, 1 over 1 plus t squared. Derivative of e to the t plus 2, e to the t. Derivative of t cubed plus t squared plus 2t, 3t squared plus 2t plus 2. Also, let's do the acceleration while we're here. Derivative of 1 over 1 plus t squared is, that is correct, negative 2t over 1 plus t squared squared. Good. Derivative of e to the t, e to the t. And derivative of 3t squared plus 2t plus 2, 6t plus 2. So, what comes next? Well, someone said cross product. We are going to take a cross product, but is that what comes next? It could, but we have two choices. What needs to happen? We have to evaluate and we have to take a cross product. Now, which should come first? Should you evaluate or should you take a cross product? Usually, if you have a choice, do the evaluation first. The sooner you can do the evaluation, the better. But you have to make sure you can do the evaluation. So, in other words, you can't evaluate before you take a derivative. But after you take a derivative, evaluation is great. So let's evaluate. R prime of 1. Well, that'll be a half e, and 3 plus 2 plus 2 is 7. R double prime of 1, well, that'll be negative 2 over 4. So that'll be negative a half, and e, and 8. All right, now we take our cross product. So I, j, k, 1 half e 7, negative 1 half e 8. And in case you're wondering, I know most of you probably aren't wondering this, but in case you're saying, do I need to take r prime cross r double prime, or do I need to take r double prime cross r prime? The answer is, doesn't matter. Just whichever one you like. You will get something slightly different, but the slightly different is a negative sign. And because we only care about the direction, the negative sign doesn't bother us. All right, let's see. We get I times e times 8. That's 8e times I. J times 7 times negative a half, minus 7 halves j. K times a half times e. That's going to be 1 half times e times k. We're going to get minus a half times e times k. So, but because we went in this direction, that'll become minus minus, which is plus a half times e times k. Then e times 7 times I, which is subtract 7 ei. And then 8 times a half times j, that'll be plus 4j, but we went in the direction which says you need to subtract it, so minus 4j, which looks like we're ending up with e in the first entry, then minus 4 and minus 7 halves. Well, that's very negative. Negative 15 halves. Wow, that is very negative. Well, sometimes you're negative, sometimes you're not. Okay, and then the last entry, it also looks like e. Okay. Well, if you're paranoid, what do you do? Yeah, you just check. Do a dot product. Okay. Minus a half times e, minus 15 halves times e. So far, if I have minus a half and minus 15 halves, that gets us up to minus 16 halves, also known as negative 8e, plus 8e is 0. So the dot product of the cross product and the original, one of our original inputs is 0. That's a sign we probably did it right. We could have checked the other one too. It'll also be 0. So this is our normal vector. If we wanted to, we could scale it. We don't have to. We're okay with this one. All right, so we've got our point, and we've got our normal vector. So we can say that our plane, well, that will be ex minus 15 halves y plus e times z is equal to, well, now we plug in our point. E times pi force minus 15 halves times e plus 2, and then plus 4 times e. And we'll be okay leaving it in that way. The rest of it's arithmetic, and unless it says simplify, we don't have to simplify. All right. Well, good. Good. So we can find osculating planes. So we can now do the following. If we have our position, so in other words, we have our r of t. If we have that, we can find velocity, and that's great. But what if we want to go the opposite? So I want to start now with my velocity, and I want to get up to something that has to do with position. So to do the opposite of derivatives, we do antiderivatives. So how do you do antiderivatives of a vector valued function, like the kind of functions we're dealing with? And, well, you think about how you take derivatives. When you take derivatives, we did it entry by entry. So when we're taking antiderivatives, we do it entry by entry. So that's good. Now, there is just one note here, which is, what about the constants? Okay. So you can think of it in a couple different ways. First off, there won't be a single constant, because you can't have a vector plus a number. Vector plus number doesn't work. But what you can think of is saying, okay, each individual entry gets its own constant. And if you work in it that way, you're perfectly fine. The other way to think about it is like, okay, I'm going to add a constant vector. So you add a vector that looks like C, D, E on the end. So let's do an example. Okay, so this is always a dangerous one. When I ask for functions for derivatives, I'm always safe. When I ask for functions for integration, well, let's find out. Okay, let's do a vector valued function.
Negative sine t.
All right, negative sine t. Somebody has picked up on my cue. Give me something that we can integrate. T squared plus 2. All right. All right, good. One more entry. Wait, what? 1 we can do better than 1. So, but we can always do a 1 plus. We have space. E? You mean e to the t, or? Okay, all right. E to the t. Okay. There was a 1 over 1 plus t squared. All right, we'll throw it. Not every problem has to have an arctangent. I just want to be clear. But it's not bad. It's a great function. Wonderful function. Some people think it's the best function. All right. So how do you do it? The answer is you integrate term by term. What's the integral of negative sine? Cosine. So, yeah, we could put cosine plus a constant here. Okay, integral of t squared plus 2. Yeah, so 1/3 t cubed plus 2t plus another constant. And notice that these are different constants. They're independent of each other. So it's not going to be, oh, I'm going to put a c in the first entry, I'm going to put the same c in the second entry. No, no, no. Each entry gets its own constant. All right, come to the last one. Antiderivative? T plus e to the t plus arctangent of t. And then plus, that gets its own constant. But again, notice that we can just separate it. So we can say, look, there's the cosine t, the 1/3 t cubed plus 2t, and the t plus e to the t plus arctangent of t. But the separation is we make the constants its own vector. So this is what we mean by the constant vector. Now, neither is like you must use this over that. It's just depending upon the context and what you're comfortable with. You should use what you're comfortable with. Now that's an indefinite integral. We can do the exact same thing for definite integration. In other words, we have bounds. So, do you want to do the same problem? We can do a slightly different problem if you want, or not. Do you have a prefer? Is there like a problem like, boy, I've been really itching to see the antiderivative of something for a while?
Secant squared.
Secant squared. Okay. 0 to 1 is just convenient, especially Secant squared, that's going to... All right. Good?
e to the negative t over t.
You have to give me something I can integrate. So maybe not e to the negative t over t. That's a great function. And if you've been hanging out with your Calc 2 brothers and sisters, that's one that they're probably banging their heads against right now. But you have to have something we can integrate. So we could do something maybe kind of like that. How about 2t e to the negative t squared? That we can integrate. Anything else? One more entry. Of what? 400? Okay. I mean, we can do it. Sure. All right. So here we go. All right, here's our function. Now, what can you think of? Well, you can think of this in a couple of different ways. You can think of it in the following way. You can say, all right, I'm going to think of this as I'm going to go through and piecewise integrate. Antiderivative of secant squared, tangent. Antiderivative of 2t e to the negative t squared, negative e to the negative t squared, and antiderivative of 400, 400t. And here, notice that there's no CDE, because when you're doing an indefinite integral, you don't need your constants. Then you can say, look, I'm going to evaluate this from 0 to 1. And then you just do the valuation. So that's tangent of 1 minus e to negative 1 and 400. Subtract tangent of 0 minus e to the negative 0 and 0. And then you can say, well, okay, certainly tangent of 0 and 0 are certainly 0. And this e to the negative 0, well, that's negative 1 over e. So I can put this back. Whoops, I forgot a comma here. Oops, sorry, that's negative 1. Sorry. I know how to math. Minus, minus. All right, so that's tangent of 1 minus 1 over e. That's where the 1 over e is. Plus 1, and then 400. An alternative way to do this is to think of it in the following way. So, hey, instead of before I do anything, I'll just say, look, this is really just saying integrate in each slot. So integral 0 to 1 of secant squared t dt, integral 0 to 1 of 2t e to the negative t squared dt, and integral 0 to 1 of 400 dt, and then just do it as you did before. So again, we get back to our thing we mentioned in our last session, which is to say, you know, when we think about multivariable calculus, it's not really new stuff. It's the same things we've learned before. We just get to do it multiple times. So now every integral problem is 3 times as many parts. But each part, it's the same ideas. And of course, we've gone a lot better, hopefully at least 3 times better, so that we'll be able to get through all these problems. All right, so let's do an example. A particle moving through space has a certain acceleration. It's 2 sine of pi t and 6t. At time t equals 0, we know where the particle is at. It's at this location 3, 0, 1. And at time t equals 2, we also know where the particle is at, 1, negative 2, 5. So the question is, what's the velocity at time 1? So I have this curve. So I'm not sure exactly what it does, but okay, so it's doing something. And I know at time 0, it's going to be at 3, 0, 1. And at time 2, so this is at t equals 0. And at time 2, it's going to be over here at 1, negative 2, and 5. And so the question is, at time 1, what's the velocity? Okay, so we're after that. Well, let's think about it. How do you go from acceleration to velocity? Yeah, take an antiderivative. You're integrating. So this looks like it's going to be a short problem. So we have acceleration. We'll write that down again. 2 sine pi t 6t. We integrate and get velocity. All right, integral of 2t. And I'll put my constants on the inside. There's no reason, but I just like them. Sine of pi t, antiderivative of that. Negative cosine of pi t. Anything else? Ah, right. Remember, you got to compensate for the pi on the inside. And then a constant. All right. Antiderivative of 6t? 3t squared. Plus another constant. All right. And now we're ready to answer our question, right? We plug in 1. So the velocity at time 1, well, that would be 2 plus c. That's the cosine pi. It's not 0. It's negative 1 times minus 1 over pi makes it 1 over pi plus d. And then 3 times 1 squared, that's 3 plus c. Okay, so is that our answer? It's not our answer. What's wrong with our answer? We still have those constants. We don't know what those constants are. We can't evaluate yet. All right. So let's think about it. How do we find our constants? Well, we need to use our additional information. Our additional information, though, is what's happening at time 0 and time 2. And these are these velocity? They're not. What are they? Position, which means we've got to keep going. So, how do we get from velocity to position? We integrate. R of t. All right. Antiderivative of 2t plus a constant c. T squared plus ct plus another constant, f. Antiderivative of negative 1 over pi cosine pi t plus a constant d.
One over pi squared.
1 over pi squared times sine of pi t. Yeah, so the antiderivative of cosine is positive sine, and then you have to divide by pi again. The negative still stays. Then for the d, what happens to that? dt, and then we add another constant. All right, go to our last entry. Antiderivative of 3t squared plus e. T cubed plus e times t plus h. Wow, good. Alphabet soup. 6 constants. Well, hopefully we have enough to figure it out. Now what do? Well, yeah, we use our data. And notice that each point of data actually has 3 values. So that's good. We actually, in some sense, have 6 numbers to work with. So that should help us get 6 constants. Now, generally speaking, my rule of thumb is 0 is a good number. So as often as you can, use 0. And if you have a choice, use 0 first. So let's plug 0 in. And the reason 0 is such a good number is it has this magical property of canceling stuff out. So when you plug 0 in, what happens to our values? What do we get? In our first entry, we get f. In our second entry, g. In our last entry, h. Well, that's FGH. That has to match up with our location 301. So we can now conclude that, reading off the entries, f equals 3, g equals 0, and h equals 1. So that wasn't so bad. Cool. So again, f will become 3, g will go to 0, h will become 1. Now we go and plug in our other data point at 2, r of 2. Well, let's figure it out. What do we get in our first entry? Okay, so we're going to get 4 plus 2 times c plus 3, which does become 7 plus 2 times c. In our second entry, Sine of 2 pi is 0. Well, that's very convenient. And so the g is already 0, so we're going to end up with just a 2D problem. Good. Last entry. So we're going to get 8 plus 1, which is 9, plus 2e. That has to match up with our location, which is at 1, negative 2, 5. That is a negative there. It's just very poorly written. It's better written over on the problem. All right, so 7 plus 2c has to equal 1. 2 times d has to equal negative 2. And 9 plus 2 times e has to equal positive 5. So what should c be? Negative 3. Because I need 7 minus 6 to be 1. So 2c has to be negative 6. What will d be? Negative 1. How about e? Negative 2. All right. Good. So the good news is C, D, and E, that was what we were missing up here. So we're going to take this information about C, D, and E and plug it into our velocity. So we can say that our velocity at 1, well, it's going to be 2 plus C. 2 minus 3 is negative 1. The next entry is 1 over pi plus D, so that's 1 over pi minus 1. And the last entry is 3 plus E. That's 3 minus 2, which will end up being a positive 1. And there we have it. So we're using information to help us solve for our constants to let us find our various points. All right. So suppose we have r prime of t, which is equal to v of t, which is equal to something. All right. Are you still willing to give me a function, or should I just make one up? Make one up. All right. Whoops, that looks like a z. 2t plus 1, let's say e to the t, and we'll say sine of t. All right. Suppose that's r prime of t. Let's find the integral from negative 1 to positive 2. And we want to interpret the answer geometrically. So here, this is not a really hard problem. This is what we've done before. So most of this is going to be like, how do we interpret this answer geometrically? So again, go through and you integrate entry by entry. By the way, if you're nervous about how complicated are these integrals going to be, I will say we pretty much shoot for Calc 1 level complication in terms of like the things you're going to integrate. We're not going to be like, ha ha ha, let's pull out a trig substitution. No, no, no. We love trig substitution, but that's not our goal here. The goal of multivariable calculus is to practice setting things up in multiple variables. And so we're not going to stress and make you panic about really complicated integrals. The integrals will be fairly straightforward. So what do you get? Well, you get t squared plus t, e to the t, negative cosine t, evaluate from negative 1 to 2. And so in the first entry, well, that'll become 4 plus 2, which is 6. Then you're going to subtract negative 1 squared plus negative 1, which is 0. Oh, that's not so bad. You get e to the 2. When you plug in 2, subtract e to negative 1. And you're going to get minus cosine of 2, and then minus cosine of negative 1. And, minus makes that a plus. Sorry about that. Oh, there you go. All right, so that's the answer. That's the integral. But here's the question. What is this? Well, let's be careful. This is a vector. Now, you might say, of course it's a vector, Steve. Everything we do is vectors now. We got rid of points. So the question is, what vector is this?
vector that goes straight from your starting point to your end point?
Yeah, so this is a vector about positions. So if you integrate r prime, you'll get r of t up to, of course, some constant. But again, think about what happens in Calc 1. Those constants, when you evaluate by taking the difference, drop out. So if you were to think about this as a curve, so maybe you have a curve here in three-dimensional space. So perhaps this is where I'm at time -1, and perhaps this is where I'm at time 2. So the integral from -1 to 2 says, well, take your position at 2, subtract off your position at 1. It's that vector that goes from here to there. That's the vector you found. So it's the vector from position at time -1 to time equals +2. All right? So that's essentially what we found. Yes? No? All right. So there's a question here. In general, if you let r of t be the position of a particle moving through space, and we can ask ourselves the question, between time t equals a and time t equals b, how far has the particle moved? Now, what's the answer? And this will be, people will argue with me about my wording here, but so I have this particle. It started here at time t equals a. It ended here at time t equals b. How far has the particle moved? Well, what you do is you look at that vector that goes in between. That's how far it's been moved. And essentially what you can think about this is the displacement. How much has its position changed? So you have this vector v, which you can find by taking r of b, subtract r of a. And if you want to talk about a length, what would you do? You could take the magnitude. Now there's a slightly different question. This question. Between time t equals a and time t equals b, how far has the particle traveled? Well, so I start here at time t equals a. I end here at time t equals b. The particle travels. Well, where does the particle travel along? It travels along the curve. So what we want is we want to find the length of this curve, or at least this part of the curve. So that's the goal in answering the question, how far has the particle traveled? Now, how are we going to do that? Well, you can think of it, if you have like a fancy thing here, you can say, suppose this is where I start at time t equals a, this is where I end at time t equals b. What you can think of is like, it would be really convenient if we could like straighten it out, because then it's really simple to measure it. And more or less, that's the philosophy about how we're going to do it. And we're going to talk about how we're going to do it in our next session, because that's it for today.